Hi, Ace Trig students. Mr. Meunier here finally. I hope we're all doing well. I apologize about last week and trying to use other videos to get us through the law of sines. I'm not going to lie, tech savviness is not my thing, and this whole extended e-learning thing is really pushing my boundaries, but I'm going to attempt to communicate with you personally. I think that's important to see how we're all doing. And hopefully if this goes well, I can start doing some live Zoom sessions later on this week. So last week, you guys did a good job, it appears, with learning the law of sines using Mr. Gayton's videos. Those quizzes look pretty good. I will put those in the computer probably today, Monday. And your right triangle quizzes look really good as well. Please make sure all those quizzes are completed. We're probably going to need to be doing some more Schoology assessments here throughout this week, and hopefully we're back in school after spring break. If not, we'll have to ramp up the Schoology assessment tool. Today I want to talk about law of cosines. Typically I would go through a proof on the law of cosines. So if you get your notes out, that was in the attachment today, I would go through this proof. I'm not going to do that just because we're a little behind. But long story short, the law of cosines is utilized for non-right triangles, and they would basically take a non-right triangle off to the side here, and they would split it into two different smaller right triangles, and they would utilize Pythagorean theorem and your CAH, the Ka part from SOHCAHTOA, to create a formula used for all triangles that are non-right. Instead of that, I want to kind of rehash what we've looked at thus far. We've looked at triangles that are right triangles. If we have a right triangle, we can utilize at any time the Pythagorean theorem or SOHCAHTOA. Those are the biggies for a right triangle. Now, on a non-right triangle, you learned the law of sines last week. Law of sines is incredibly simple and powerful to use. To make that work, though, we need angle and opposite side to set up our ratios. We need an angle and an opposite side to make that happen. If you don't have an angle and opposite side pair, law of sines is hard to use. It's impossible to use, which is why we need another law of cosines to make this happen. And you would have learned there's some issues with law of sines. You have an ambiguous case where two triangles could be possible. That's not ideal. Law of sines also does not work well for obtuse triangles. This does not work well with obtuse triangles. Why that is, real quick, if you think about our inverses, if I'm trying to find an angle and I have to take the inverse of something, we learned in chapter 7 that inverse sine only has answers in quadrant 1 or quadrant 4. And if you think about a triangle, triangles have angles that go from 0 to 180. Quadrant 2 is not going to happen. An obtuse angle, an angle bigger than 90 degrees, does not appear when you use an inverse sine function. Therefore, the law of sines is not going to help us figure out obtuse angles and obtuse triangles. It will only tell you acute angles between 0 and 90, or it's going to tell you quad 4 angles, which don't exist in a triangle, which is not going to happen for us. But fortunately, cosine as a function has solutions in quadrant 1 and quadrant 2. So that gives you your 0s, your 90s, and your 180s all pop up if we're going to use what's called the law of cosines, which we're going to get into today. Now with the law of cosines, whoopsie, sorry about that. It's a complicated looking formula. Typically in class, I would give these things to you. I would never ask you to memorize these formulas. Now that we're kind of at home doing stuff, it's kind of a Wild West free-for-all where you guys are using your calculators and probably having notes out and examples out with you as you take quizzes. I can't really police that right now. But with the law of cosines, I notice basically one big thing here. No matter how you set it up, the angle and side are apart from each other. So little a is the side, big A is the angle. They're on the edges. The other two sides are kind of sandwiched in the middle, BC, BC. So a squared equals b squared plus c squared minus 2bc times cosine of a. B squared equals a squared plus c squared minus 2ac cosine of b. So again, there's your b's. Opposites pairing up on the edges, the other two in the middle. And then the c squared equals a squared plus b squared minus 2ab cosine of c, where again, opposites are on the edges here, other two are in the middle. And if it's not an ABC, we can apply this to any triangle. XYZ triangle could be X's on the edges, Y and Z sides in the middle. That's how I always remember this. The pair together on the extreme edges, other two sides in the middle. So how's this going to look? How are we going to attack this? Now let's try to solve a triangle. I always like to get a picture going here. We have triangle. Side B is 5, C is 8, angle A is 35. So triangle A, B, C, little a, whoopsie. Sorry about that. Little a, little b, little c. Side B is 5, side C is 8, angle A is 35 degrees. We got to figure out angle B, angle C, and side A. This is not a right triangle. Nothing says right triangle. I can't assume a right triangle. Therefore, Pythagorean theorem cannot be used. SOHCAHTOA cannot be used. I can't use the law of sines from last week because I do not have an angle on opposite side pair. I have angle A, but it's not side A. I have side B, but not angle B. I have side C, but not angle C. I don't have that relationship. But I can figure out side A because I know angle A and I have side B and C. So I'm going to attack that first. Side A, where I can say A squared equals B squared plus C squared minus 2BC cosine of A. I plug things in and we get A squared equals 5 squared plus 8 squared minus 2 times 5 times 8 times the cosine of 35 degrees. And I can plug this in my calculator. I can go 5 squared plus 8 squared minus 2 times 5 times 8, whoopsie, times 8 times the cosine of 35 degrees. I'm also in degree mode here. I don't want that. That gives me an answer of about 23.4678. So that's A squared. I want A, so I can take the square root of that answer. And you get about 4.8 for side A. Okay. Now, at this point, I have an angle, an opposite side pair. I know angle A is 35 and side A is 4.8. Because of that, I can use the law of sines. I want to be strategic about this though, because like we said, law of sines does not work for an obtuse angle. A triangle can only have one obtuse angle if it has any at all. Therefore, I'm going to use the law of sines to figure out angle B. I'm going to pick angle B because it is the smaller angle. If there's an obtuse angle in this problem, it's going to be angle C. The largest angle is always across from the largest side. Side C is 8. Therefore, angle C might be obtuse. I'm going to make that note. Angle C could be obtuse. Do not use law of sines on it. Do not use law of sines. But angle B cannot be obtuse. You cannot have two obtuse angles in a triangle. So I can use law of sines to figure out angle B. Maybe. There. Oopsie. So let's figure out angle B. I'm going to do and say the sine of 35 degrees for angle A over 4.8 for side A equals the sine of B over 5 for side B. That's going to give me 5 sine of 35 degrees over 4.8 equal to the sine of B. So the inverse sine of 5 sine 35 degrees over 4.8 equals B. I go to my calculator. Again, we're going to have the inverse sine trig inverse sine of the fraction of 5 times the sine of 35 degrees divided by 4.8. And I'm already in degree mode, so I have an answer of 36.7. And then once I know those two angles, I can figure out angle C pretty quickly because all three angles add up to 180. We can say 35 degrees for A plus 36.7 for B plus C is 180 degrees, which is going to give us 180 minus 35 minus 36.7, which is roughly 108.3. And because of that, my bad. The screen is very touchy. Let me fix this up. Angle B is 36.7. And angle C is 108.3. So there you go. Again, long story short, we have a non-right triangle. Pythagorean theorem, SOHCAHTOA cannot be used. The law of sines was not an option initially because I did not have an angle on opposite side pair to work with. Law of cosines, the new law allowed me to figure out side A. From that, I now had an angle opposite side pair where law of sines was an option, but I wanted to be strategic and find angle B because it was not going to be obtuse. Law of sines does not work for obtuse angles. If I would have used law of sines to find angle C, I would not have got 108.3. All right, one more. So now, Solve triangle. A equals 6, B equals 8, C equals 5. I'm going to draw a picture. A, B, C. A is 6, B is 8, C is 5. Not a right triangle. Cannot use Pythagorean theorem. Cannot use SOHCAHTOA. Law of sines will not work because I do not have any angles to set up an angle opposite side pair. I have to use the law of cosines to find one of my angles, and I want to be strategic about this. Law of cosines works for anything. Let's do it to find the biggest angle. So I'm going to say, if you have to use the law of cosines to find an angle, use law of cosines to find your largest angle. Only one angle in a triangle can be obtuse. So use the law of cosines to figure out that potential obtuse angle. Looking at this, if we have an obtuse angle, angle B could be obtuse. Side B is the largest side, thus angle B has to be the largest angle. So angle B could be the obtuse angle. So I'm going to find angle B. I'm going to use B squared equals A squared plus C squared minus 2AC cosine of B. I know side B is 8. I know side A is 6. I know side C is 5 minus 2 times side A is 6. Side B is 8. Cosine of the unknown angle B. So 64 equals 36 plus 25 minus 6 and 8 is 46 times 2 is 96. Cosine of B. Combined terms here. 36 plus 25 is 61 minus 96 cosine of B. Do not subtract the 61 and 96. Subtract the 61 over. 3 is negative 96 cosine of B. Divide the negative 96 over. So negative 3 over 96 is cosine of B. Take the inverse of that. So the inverse cosine of negative 396 should equal B. Now you can reduce that. You could get negative 1/32. That's not a big deal. Go to the calculator. I'm going to go inverse cosine of negative 3 over 96. And again, make sure you're in degrees. Whoopsie. And we get about 91.8 degrees. So it is an obtuse angle. It would not have worked if we use the law, if we try to use law of sines on this angle. So now that I have that angle opposite side pair, I can figure out angle A, and I know angle A is not obtuse. There's only one obtuse in a triangle if it has any, and I can use the law of sines real quick. We can say the sine of 91.8 for angle B over 8 for side B is the sine of the unknown angle A over 6 for side A. Multiply the 6 across. 6 sine 91.8 divided by 8 is the sine of A. Take the inverse of this, and that should tell us angle A. So inverse sine of 6 times sine 91.8 divided by 8. So calculator, inverse sine of 6 times the sine of 91.8 degrees divided by 8 gives you about 48.6 degrees. And from there, we can quickly figure out angle C, because again, we know, I hope we know, all three angles of a triangle add up to be 180. So 91.8 plus 48.6 plus C is 180. So angle C would be 180 minus 91.8 minus 48.6. 180 minus 91.8 minus 48.6 gives us roughly 39.6. And that does make sense. Again, if you compare largest angle is opposite largest side, smallest angle is opposite smallest side. The two smaller angles are fairly close because the two smaller sides were fairly close to each other. All right, that's what we're going to break today. For your assignment out of your book, please try to complete, as of now, page 537, number 17, 19, 31 to 35, odd. 17, 19, 31 to 35, odd. And that'll also be written in your announcement for the day. All right, guys, have a good day. Bye.